All right, we're going to wrap up Chapter 2, our study of sets, with a section about cardinality. Now, we've already defined cardinality and had some theorems dealing with cardinality. So that's something that we'll have to kind of build on here. But this section is going to introduce some more ideas that I think are kind of fun. They play a very sort of very special role in sort of pop mathematics. I think that a lot of people get a little bit excited hearing about the idea of levels of infinity. And this is the section, this is the point where we get to really learn about levels of infinity and what that is. Or at least we get to learn about it from one perspective, which is the idea of cardinality of sets. So first of all, I have a reprise of a theorem from last section that I put up here. So this is not the entirety of the theorem. This is in the previous section I wrote these, and I also wrote their contrapositives just so that we could kind of understand it from both angles. But here I just have these. So let's review. If you have two sets A and B, if there exists a surjective function from A to B, right? So if it's like possible to make a surjective function from A to B, then that means that the cardinality of A has to be greater than or equal to the cardinality of B. All right, so remember, if it's possible to make it surjective, then you have to have at least as many things in A as in B so that you can cover all of the elements in B with arrows, so to speak, right? Now, on the flip side, if it's possible to make an injective function from A to B, right? If you can make it 1-to-1, well, then you have to have no more elements in A than you have in B, right? So the cardinality of A actually has to be less than or equal to that of B, right? To make it possible to map 1-to-1. And then putting those two ideas together, if there exists a map from A to B that is bijective, a bijection meaning both surjective and jective, it must be both, the cardinalities, you must have both greater than or equal and less than or equal, which leaves only one option, they must be equal to each other. Now, this doesn't mean that every map is going to be a bijection between two sets of the same size. And none of these are saying that every map, it's just saying that there exists a map. If it's possible to make one that is a bijection, then you can prove that the sets are the same size. So we actually take that third part not just as a theorem, but really more so as like the definition of equal cardinality. Okay, we define equal cardinality as saying that there exists a bijection f from A to B. Okay, so with that, just as our starting reminder, let's get to one of the main topics of this section, which is the idea of countable sets. So, what does it mean for something to be countable? It means that it's possible to count it. I'm just going to draw some shapes here, and then we're going to count them together. All right, this is, we're going to imagine that you are like 3 again, and learning how to count. Okay, I don't mean that to be in any way, insulting or anything like that. I actually have a 3-year-old, and I find it fascinating how he learns to count. So let's say that you have this set of things, and maybe it goes on for a while, right? Or no, maybe it doesn't. No, yeah, and let's just say it goes on for a while. So when you're counting these things, what you're doing is you're pointing at them and saying numbers, right? Like I'm gonna say, hey, this one here, this is gonna be number 1. All right, and then this one here, this is gonna be number 2. Okay, when you're helping like a young child learn how to count, you have to really teach them this idea that if you're trying to count a set of objects, you don't count the same object twice. So I'm not going to say, count 3 and then go back and count 4 on a previous object, right? Because if you label this one 4 where you already labeled it 2, right? Then that would be creating a function from these integers to these objects that is not injective, right? So when we tell a child when they're counting, when they're learning to count, when we tell them that they shouldn't count the same object twice, that is telling them that the function they are forming by labeling these objects with numbers needs to be injective. Okay, so we continue to map our integers to our objects in a way which is 1-to-1, And the other thing you need to make sure that you do is count all of them, right? Like if you're trying to count this set of objects and your child who you're helping, if they stop before they get to all the objects, then you say, well, you're not done counting. You've got to keep going. Keep mapping. Keep creating maps that go to keep creating these labels where you're mapping the next number in the sequence to the next object in the set. That is like telling them that they have to be creating a map which is surjective, right? It has to cover all of the elements in the output codomain, as it were. Okay, so I'm trying to what I'm saying here is that counting, like the simplest idea of counting, labeling objects with numbers in a one-to-one correspondence, is creating a bijection. So when we define the idea of countable, when we define what countable is, we're going to use this idea of creating a bijection. So we're going to say that a set A is countable if one of two things happens. One, it's finite, right? So if its cardinality is a natural number, right, then which is what finite means, then that's countable. Or two, there exists a bijection f from the positive integers to that set A. A bijection. Okay, and the reason it's coming from the positive integers is because the positive integers are the numbers that we use to count with, right? 1, 2, 3, 4, 5, 6, so on. You start counting with 1, at least I do. Maybe if you're a programmer, you start counting with 0, which would be the natural numbers. But we're going to go with positive integers because that is the most natural approach here. So a bijection, and that, if that happens, okay, if the entire set of positive integers can be mapped to the set, well, because the set of positive integers goes on forever, right, because it is infinite, this situation is called Countable Infinity. So the types of countable situations are any finite set, that would be called a countable set. You can count something which is finite, or if it's infinite, as long as it is in one-to-one correspondence with the set of positive integers, the numbers we use to count things, then we can call it countable.